Okay, so let's work on this problem now. So in the previous equation, we want to take u of xt being equal to 1 plus x, and we want to use the method of characteristics to solve this equation. Let me just give you I'm going to give you one warning. Actually, let me give you one physical setup for something this might potentially model, and then give you one warning. So what is the physical setup that I'm thinking about here? So imagine there's a wind tunnel. There's a wind tunnel, and the velocity of the air at location x is u of x is equal to 1 plus x. So if you look at kind of a side view of this, you've got a wind tunnel, the air is moving in this direction, and we know that the velocity of the air, because we've set the wind tunnel to do this, however that happens, I don't know, I don't do wind tunnels, we know that at every point the velocity is 1 plus x. So it's the air speeding up as it goes along the wind tunnel. And what we want to do is kind of the rho of x now. We can imagine the rho of x. It's modeling, let's say, like dust particles that are going to be carried along by the air, but don't really affect the velocity of the air. So rho of xt, this is going to be, I don't even know if this is a unit, nanograms per meter. That's the density of the dust particles. There's rho of xt nanograms per meter, so very fine, small amount of dust. And the rho of x0 equals x from x going from 0 to 1 and 0 elsewhere. Let's say this is 1 here. It means we're going to have, the concentration is going to be 0 at the left end, and it's going to be very high at x is equal to 1, and then kind of gets a little bit more and more as we go on. And so from 0 to 1, there's a 0 concentration here. There's a concentration of 1 nanograms per meter there, like instantaneous concentration. And then, it's going to ramp up from 0 to 1 there. Okay, so the warning that I want to give you, rho is the unknown. And u is velocity. Okay, I'm saying that because typically up until now, u has been the unknown, and I actually did this whole video with u being the unknown and the velocity, and I wasted a whole bunch of time, so I don't want you to make that mistake. I made it, it's easy to make. This is just sort of the conventional notation that gets used. There's reasons for that, because often u is also unknown. U is going to be the velocity field for something, and if it's unknown, it also makes sense to call it u, and rho typically is used to denote the density, and so it also makes sense to call the density rho. Sorry, I had to plug in my laptop. Okay, so remember the equation, the general equation, is going to be partial t rho plus partial x rho u is equal to 0. But now we know what u is. We know that u is equal to 1 plus x. And so now the equation, what I get, well, even without knowing what u is, if I just do the product rule for the x derivative, this is partial t rho plus partial x u rho plus u partial x rho is equal to 0. Okay, so if I rearrange this to make this look a little bit more like the PDEs that we deal with, we're going to have partial t rho, and then this term right here, that's going to be 1 plus x because u is 1 plus x. So it'll be 1 plus x times partial x rho is equal to minus this term, but the x derivative of u is just 1, so it's going to be minus rho like that. Okay, now as usual, t dot is going to be the coefficient on the t derivative of rho, so that's 1. T of 0 is going to be equal to 0. If I look at x dot is going to be the thing multiplying by the x derivative of rho, so that'll be 1 plus x, and this will be x naught. Again, as usual, the z dot this is z dot. So then z dot is equal to rho, but along the characteristic curve, z is just equal to rho. So this is minus z. And z of 0, well, I'm just going to write now, z of 0 will be rho of x naught 0. And there's going to be two cases. This is going to be x naught if we've got 0 less than or equal to x naught, less than or equal to 1, and it's going to be 0 else. Okay, so now let's get to work to solving these equations. So if I look at t, if I look at my equation for t, this is going to tell me t of s is equal to s. If I look at my equation for x, this is going to be x dot is equal to 1 plus x, or if I can rewrite this as x dot minus x is equal to 1. Okay, and this is a first order linear differential equation. You can use it, you can solve it by using integrating factor, and the solution is x of s is equal to x naught plus 1 e to the minus s minus 1. And then finally, the equation for z is going to be z of s is equal to z of 0 e to the minus s. And then this is either going to be, I'll write it this way, it'll be e to the minus s times x naught if we have 0 less than or equal to x naught, less than or equal to 1, and then 0 else. So we could write this in the following way. It'll be e to the minus s times x naught if 0 less than or equal to x naught, less than or equal to 1, and it'll be 0 otherwise. Okay, so now next, as usual, we want to try to write the solution in terms of a's and b's, but I first want to do something that I've usually already done at this point, which is to sketch, to do some sketches. So again, this is going to be the y-axis, and then I'll call this one right here. This will be the x-axis. And what are we given? The information that we're given is I know what rho is, or I know that rho is equal to x naught from 0 to 1. And then I know after that, the initial value for rho is going to be 0. Okay, so I'm given that rho is equal to x naught from 0 to 1, and it's equal to 0 for all other values of x. Just the initial condition. And then I also can continue the red going this way as well. So now let's look at our solutions. If I look at the characteristics, if I look at the characteristics, I've got, oh sorry, this there's a typo here. That should not be minus s, this should be plus s. Okay, so I had a typo there. I'm going to do it in purple so that you can see where the change I made was. Okay, so let's think about what the characteristics are going to look like. The t value, that is the t coordinate, is going to be s, and the x coordinate is going to be an exponential function of s. In other words, the horizontal coordinate is an exponential function of the vertical coordinate. So we think about how we normally think about things. This is going to be like a logarithmic type of curve in the xt plane. Just for the sake of labeling, this is the x-axis, this is the t-axis. So the curves are going to look something like this. And you can look in Desmos if you want to see an even better example. And then so similarly, the curves here are going to look like this. And the curves starting here are going to look like this. Okay, so this kind of divides the plane into two different regions. We have the purple region. This consists of points, we'll call this AB. This consists of points such that if you look on their characteristic and trace it back to the purple and trace it back to the x-axis, the solution is not going to be 0. So we're in the purple part where rho of x naught is equal to 0. And then we'll have the other part of the plane. It could be either like here or right here. And what happens for these points, if you look at the characteristic through them and trace that back to the x-axis, you get the part where there, in the initial distribution, there isn't anything. And so let me just give you a preview of what's going to happen. If I consider, say, this point right here, And if I'm just looking at this point, this looks like it should be x is equal to 2. If I look at this point and look at this vertical line right here, like that's going to be what's happening at, like as we go along, as you go up in the vertical direction, that's going to be the direction of increasing time. So if I stand at this point right here, and I just look at what happens at increasing time, as long as that vertical line is passing through a red characteristic, the solution is going to be 0 then. So I'm going to kind of have this first crossing. So this is going to be the purple line right here. So if I look, again, not everything is to scale here. So if I look, I'm looking, time is increasing, still 0, still 0, still 0. When I get right there, that's going to be the first time that I see dust particles coming by if I'm just observing at the position x is equal to 2. And then as I go on, what's going to happen, so this will be this characteristic here. As I go on, what's going to happen? Well, the dust cloud is going to gradually pass by. And when I get to the next red one, it's going to be 0. So along these purple characteristics, so along the beginning along the red characteristics, it's going to be 0, 0, no dust, no dust, no dust, no dust. All of a sudden, the particles of dust start coming. It's going to be, as time goes, there's going to be dust here, dust, 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 dust. And then all of a sudden, or not all of a sudden, but eventually the dust will pass by. And now once the dust cloud passes by, I'm going to see no dust for the rest of eternity. Okay, and similar things are going to be true for other values of x as well. Okay, so let's just look through this. I want to actually get what the solution is. So u of AB. Okay, well, unfortunately, the surface pin stopped working, and now I'm back to having to look at the childish or serial killer handwriting. It also meant I had to unplug my external microphone, so the audio quality probably has gone down, so apologies for that. Okay, so I want to know u of AB for some point. So let's do the purple characteristics first. If I'm in the purple region, and I'll describe these regions, the purple region and red region, in terms of inequalities, but if I'm in the red region, the solution is going to be x naught e to the minus s, and now I need to figure out what x naught and s are in terms of a and b. Well, I know that b is equal to s, so t of s is equal to b. B is the second variable, the t variable, so b is equal to s. And I know a is equal to x naught plus 1 e to the s minus 1. Well, e to the s, that's just e to the b. So this is x naught plus 1 e to the b minus 1. And now if I solve this for x naught, I'm going to get x naught, that's minus 1, x naught is equal to a plus 1 times e to the minus b minus 1. And so for the purple region, I'm going to have, and I'm just going to, well, keep it as a and b now. U of AB is equal to x naught, which is a plus 1 e to the minus b minus 1 times e to the minus s, so that's times e to the minus b. Okay, now for the red region, remember, for the red region, you've got u of AB is going to be equal to 0, because if I'm in the red region, it's going to be 0. This is the red region here, because it means I'm on this characteristic, I trace it back to the initial value. The initial value of dust there is going to be equal to 0, and so at this point right here, u of AB is going to be equal to 0. Okay, and so now what I want to do is I want to try to figure out how to write this so that I'm not writing, in the purple region and the red region. I actually want to describe this in terms of sort of, standard inequalities or something like that. So let me just first write u of xy. Okay, if I'm in the so-called purple region, this will be x plus 1 e to the minus b minus 1 times e to the minus b, and I'm going to be 0 here. And now I just realized I have gone to b. So let me, and this should be t, not y, so sorry about that. Okay, so how am I in this region? Well, I'm in this region if I've got 0 less than or equal to x naught, and that's less than or equal to 1. Well, I know how to write, I want this to be in terms of x and t, but I know how to write this inequality in terms of x and t because I solved for x naught in terms of x and t, or a and b, above. So if I look at my expression for x naught, I've got x naught is equal to this right here. So it's going to be when I've got x plus 1, e to the minus b minus 1. I've got 0 less than or equal to x naught, and this is less than or equal to 1. So maybe we can make this inequality look a little bit cleaner. If I add 1, if I look at this inequality, let's do a little scratch work. I add 1 to both sides of the inequality, or all throughout the inequality. I've got 0 less than or equal to x plus 1 e to the minus t less than or equal to 2. And again, this should be minus t. Sorry once again. I'm going to blame it on the pin not working. And then if I want to write this, I could write this perhaps as e to the t, just multiplying by e to the t and subtracting 1. E to the t minus 1 is less than or equal to x, is less than or equal to 2 e to the t minus 1. Okay, and so I'm going to have e to the t minus 1 less than or equal to x less than or equal to 2e to the t minus 1 and 0 else. Okay, so this is kind of like the analytic solution, but it's also good if we kind of look at what's going on graphically. So I want to see what's going on graphically down here, and that's what this next image is about. If I look at this image here, I want to talk about, you know, how what this diagram here has to do with the solution. So let me talk about that a little bit. So this red curve here, this red curve represents the function. This represents the function. Well, so not the function, but this is the curve x equals 2e to the t minus 1, and the blue curve represents x equals e to the t minus 1. And so again, what happens if I just camp out at the position x is equal to 2, for the first however many seconds, it looks like 1, 2, it looks like this is going to be 0.2. For the first 0.2 seconds, there is no dust. All of a sudden, when I get right there, there is dust, and it's going to be a non-zero amount of dust. It's going to go from being no dust to something more than dust. So there's going to be sort of a discontinuity along this line here. And then as I go, I'm going to see the dust cloud pass by until I get to this point right here. And at this point, the dust cloud is 0, and then there's going to be no dust after that. Okay, that's it for this video. In the next video, we're going to analyze this equation a little bit more and talk about a little bit more about conservation.